Hi there! Suppose you ride your bike eastward for 40 minutes at a constant speed of 20 kilometers per hour. Then you take a 10-minute break and finally you ride your bike westward again for 40 minutes and again at a constant speed of 20 kilometers per hour. Where are you at the end of this? Well, obviously you're back at your starting point. And we didn't even have to calculate where you went in between. We just used symmetry. Symmetry can be a very useful property. It often allows for simplifications and it makes things a lot easier. Another example, consider a mass on a spring without any friction. It will move down and up and down and so on. Well, the time it takes to make one down movement is equal to the time it takes to make one up movement. In physics, symmetry is everywhere. This video will be about a specific kind of symmetry. That is, symmetry with respect to the vertical axis or with respect to the origin for the graph of a function of one variable. Let's start with this example. F of x equals x to the fourth power plus 1. Looking at the graph, we see that the vertical axis is an axis of symmetry. This means that if we take any point on the graph and reflect it across the vertical axis, we should again find a point on the graph. Let's do this. Take a value x in the domain on the horizontal axis. We then find the point x f of x on the graph. After reflection across the vertical axis, we end up at the point which has still the same y value, but the opposite x value. It is the point minus x f of x. But the function value at minus x is by definition f of minus x. This means that in order to have this symmetry, we need that f of minus x equals f of x for all x in the domain of f. Let us check whether we can find this symmetry by using the formula. Computing f of minus x, we find that it is equal to minus x to the fourth power plus 1 is x to the fourth plus 1, which is indeed f of x. We call functions with this kind of symmetry even functions. Alright, let us switch to the second case and consider this example, g of x. G of x is 2x cubed minus x. We notice a different kind of symmetry in the graph of g. Now there is a symmetry with respect to the origin. Indeed, if we take any point on the graph and reflect it through the origin, we again find a point on the graph. What does this look like using symbols? Well, consider again a general point, x g of x, on the graph. The reflection through the origin flips the sign of both coordinates. We end up at the point minus x minus g of x. The function value at minus x is of course g of minus x. So the condition for this symmetry becomes g of minus x equals minus g of x. Again, let us check the symmetry by using the formula. G of minus x equals twice minus x cubed minus minus x, which simplifies to minus 2x cubed plus x. Putting the sign in front, we see that it is indeed equal to minus g of x. We call functions with this kind of symmetry odd functions. Now, you may find it strange to use those words even and odd, because you know even integers and odd integers, but here we are dealing with functions. Well, there is a connection. Did you notice that in the first example we could write f of x equals x to the 4 plus x to the 0? And in our second example, g of x equals 2 times x to the 3 minus x to the 1? That is no coincidence. If a polynomial function only has terms with even powers of x, then it is an even function. If a polynomial function only has terms with odd powers of x, then it is an odd function. Some other well-known functions have these symmetries as well. One look at the graphs of the cosine and sine function probably convinces you that they are even and odd respectively. Can you also show this using the formula we just saw? And maybe you can think what happens with the tangent function. Be careful though. Not all functions are odd or even. Any polynomial which has both terms with even powers and terms with odd powers is neither even nor odd. Or take the exponential function. It is not even, it is not odd. For these functions that are neither even nor odd, there is a very nice property though. Consider the function h on the right hand side. You can very easily write it as the sum of an even and an odd function. The function in black is the sum of the even function in orange and the odd function in blue. Please check this both on the graph and in the formula. It is very easy to check this property for polynomials, such as in this example. It is, however, not restricted to polynomials. Consider again the exponential function. It can be written in a unique way as the sum of an even function in orange and an odd function in blue. Don't worry too much about these specific functions for now. Later on, we will study these in much more detail. Finally, there are a lot of properties that appear by combining even and odd functions. What can you say about the sum of two even functions? Or the product of an even and an odd function? Or maybe the sum of an even and an odd function? And there are many, many more combinations like that for you to think about. See you in class!